Thank you very much, Satoki. Let me first start by apologizing. I have a very bad cold. I haven't been sick in a long time. It just started getting really bad after I came to Taiwan. Not because of Taiwan, because of all my previous travel. So I have to speak more softly than usual. Okay? When looking at my computer, I realized this is colloquium number 6 I've given at ASIAA. And it's the first time I'm talking about a subject I know very little about. For those of you who know anything about my previous research, it was always on the nearby universe, nearby galaxies, relatively inefficient accretion, star formation, things of that nature. But today I will take you on a journey to the highest redshift that are being probed with the James Webb Space Telescope. Not because I'm an expert, but just because this is too exciting to keep to myself. I would like you to know the momentous developments in the last 3 years that lead us to understand not just the formation, and I emphasize the word formation, of supermassive black holes, but also the galaxies that then grow around them. Okay, it's a paradigm shift. Much is still being debated. On average, there's about 1.7 papers a day on the archive. 2025, there were 7 international conferences held on topics of this nature. People argue passionately. So I want to share with you some of the things I've learned. Not that I really understand them. Okay, so that's the intent today. But before I take you to the very early universe, let's start with the local universe as a 0 point, because ultimately the high redshift has to evolve into what we know locally. We know 3 facts about black holes in the local universe. The first is that galaxies that have a bulge, okay, say ellipticals, early type spirals, okay, these galaxies, a very large fraction, 60, 70, 80% have weak AGNs. To the extent that AGNs signify accretion into a supermassive black hole, this sets a lower limit on the occupation fraction of supermassive black holes in the local universe. This was done before the work from Hubble Space Telescope. Okay? So I don't have masses, but I know they have black holes. When HST was launched and then refurbished, I joined the team that was responsible for using HST to search for and ultimately do a census of supermassive black holes in the local universe. And what we found is that in massive galaxies, say larger than 10 to the 10, all of them have a supermassive black hole, 100%. We never failed. Every object that we looked at a lot over several years, had a supermassive black hole, 10 to the 6 to 10 to the 10 solar masses. That was truly unexpected. We expected to see some, to the extent that quasars existed. Some dead galaxies locally should have dead black holes, but not all of them, right? So that was very important realization. And then a few years later, with the help of Jenny Green, who became my student, she found that even in low-mass galaxies, including dwarf galaxies, the ones that have black holes in the range of 10 to the 4 to 10 to the 6 solar masses, what we call intermediate mass black holes, is at least 50%. That's a lot, okay? So on average, your typical galaxy in the local universe, the majority of them have a central black hole, non-stellar black hole, right, of one type or another. So this is very well established, enough for us to write these 3 annual reviews. So all of this happened here in the local universe. We know that, of course, the activity and the growth really happened during cosmic noon between redshifts 2 to 3. And therefore, the early formation evolution had to have been even higher. So this has been the holy grail for many people for decades to search for ever higher redshift quasars. 5, 6, 7, okay? This is a record holder until recently, a redshift 7.6. And what you will find is that, so first, they're very rare, okay? So this is a log scale, right? So the space density is very rare, but they have already very large black hole masses, 10 to the 9. The record holder is more than 10 to the 10 solar masses. This has been a great challenge. It's exciting, but how do you do this? Okay, so how do you get to masses of 10 to the 9, 10 to the 10 solar masses by, the universe only had less than 1 billion years after the Big Bang, right? So it depends greatly on how it started. What were the seeds? Are they light seeds or are they heavy seeds? Light seeds would be, say, 100 solar masses. That's what stellar evolution can produce. We now know this through LIGO, for example, right? But if it's a stellar mass light seed, in order to get from here to there, you cannot obey the Eddington limit. You have to violate the Eddington limit, and essentially continuously, okay? Several 100 million years. Nothing tells us that this is impossible, but people suspect that this is highly improbable, because the growth of the black hole releases a lot of energy, radiation, momentum, which tends to have feedback on the environment that prevents this type of continuous super Eddington accretion. Anyway, but this is still a viable path. It would be easier if you start off with a heavier seed, say 10 to the 4, 10 to the 5 solar masses. So you can make, for example, from runaway mergers in the central regions of a dense cluster, or from so-called direct collapse mechanism. If you can achieve that as your initial condition, then you can sort of meander up, to the supermassive territory, even at sub-Eddington rates. Okay. The trouble is that there's very scant observational evidence to support one or the other until recently. Okay, so this is a part of the recent excitement, but this has been the famous plot, for a long time. Okay. Now, aside from black holes being very common or even ubiquitous in the local universe, the other thing that was much talked about is that they correlate quite strongly with the properties of the host galaxy. The mass of the black hole scales with the stellar mass of the bulge, almost linearly, and the mass fraction is 0.5%. It's a small number, but it's within the scatters about factor 2. Okay, it correlates even stronger with the velocity dispersion of the bulge. This is the famous M sigma relation. I won't talk about any of these things. This is the old story. Okay, but basically, these are inactive black holes in the local universe. They obey these tight scaling relations with the host galaxy properties. Okay, very 20-year-old story. Well, these are the inactive black holes. That is, black holes that are essentially not growing. What about black holes that are still growing in the local universe? We call them type 1 AGNs and quasars, okay? And it's a lot of data here, but let's just focus on this. This is the black hole mass versus host galaxy stellar mass. In gray is the reference I just gave you for dead black holes. So the active black holes, these colorful contours, are basically the same. Okay, there's a more scatter, maybe slightly, but that's just, these are less accurate estimates. Okay, but basically there are no gross differences either in terms of the mass plane or the M sigma relation. So to zeroth order in a low redshift universe, whether the black holes are active or inactive, they obey similar scaling relations. These ideas, these preceding papers, have like 12,000 citations, because it's been the favorite tool for theorists who work on galaxies and structure formation. They swear up and down, multiple generations of hydrocodes from early ones to recent ones, and without it, catastrophes ensue. Okay, you cannot explain why star formation is so inefficient. Okay, what the heck, 16% baryons and the peak is at 3%, in stars, okay? And then it's even worse for high mass galaxies. So how do you do that, right? How do you stop cooling flows from cooling all the way? Answer, some radio source, BCGs. How do you turn galaxies off, How do you quench them? And so on and so forth, okay? So there are a zillion papers that invoke the general theme of so-called coevolution or AGN feedback. The purpose of my talk today is not to critique this body of work, but just to let you know that it's very widely invoked. Okay. So everyone wants to know. So this is the situation in the local universe: tight relation of dead black holes between black hole mass and bulge mass. Well, what about at higher redshift? When were these relations first established? So this is a situation before JWST and in the very early days of ALMA, okay? And I already summarized this with John Cormandy in our review. The gray line here again is that local 0 point. And you can see that for the largest sample I could find at the time of redshift 2 even to 7 quasars, all these blue points, very, very symbols, okay? First, there is a correlation. It's not tight. I wouldn't bother trying to quantify, whatever, okay, but it's not random. But the most noticeable thing is that the 0 point is higher. So at high redshift, for a given galaxy, the black holes are overmassive. Not ridiculously, it's like a factor of 2, or maybe 2.5 or something like that, but it is systematic, okay? So in the ensuing decade, a lot of work has been initiated to understand how do you go from here to here. Okay, so on to the new stuff with JWST, right? So JWST has basically opened a completely a new frontier, not only because it's a 6.5 meter telescope, obviously bigger than Hubble, but importantly, it works in the near to mid-infrared, so that even at these very high redshifts, you're still able to probe the rest frame optical. That's important because that's where the peak of the SCD of stars are. So if you want to understand the galaxies and then the host galaxies of quasars, you want to be working at least in the rest frame optical, better yet, rest frame near infrared, right? So that's really important. Putting it L2 makes it extremely cold, okay? So, and, having 6.5 meter gives you an exquisite PSF of 0.06 arc seconds. Okay, so these are all amazing advantages to JWST. Numerous breakthroughs in every conceivable field. But I'm going to focus on one. And the initial discussion grew from data like this. This is the Sears field. It's 7 bands from the NIRCam camera. So you have basically very good colors. Again, really, really deep, very high resolution. And people were actually initially looking for compact, massive quench galaxies. So looking for something, red and dead, okay, at high redshift. This is Ivo Labbé, okay? But they stumbled upon something else that became the rave of the town. This is the phenomenon that has now been, I think, forever. This name will stick, okay? It's called the little red dots. So for the rest of my talk, I will give you a quick summary of what I think they are and what they're good for and what we've learned, okay? The reason they're very excited is that they think this is closely related to the long sought after progenitors of quasars. Okay. So first, what are they? So as the name implies, they are compact and they are red. They literally have red optical colors. So it's a very aptly chosen name given by Matthew. But let's be more quantitative. Okay. When I say compact, I really mean compact in the sense that they are unresolved. The best cases are completely, utterly unresolved. despite the exquisite PSF and sensitivity of JWST. And the best study cases are further magnified by gravitational lensing, so you can even get better constraints. The effective radii of about 20 to 30 parsecs. That's really extreme. Okay, that's like a big star cluster. That's smaller than an OB association in the Milky Way. Okay? And it's unresolved. Okay, so it could be smaller than that. And in some of the best study cases, this being one of them, you can stare at all you like. You can use whatever analysis method you want. You can stack to your heart's content. You will find that these objects are absolutely isolated. There's nothing around them. Okay, to exquisite limits. Okay, within less than 30 parsecs. That is truly mind-boggling. Okay. The other very distinctive characteristic is the broadband spectral energy distribution, the SED. So here are the 7 bands of the NIRCam camera. And you can see that there's this characteristic V shape. Okay. The break here is roughly at 4,000 angstroms, rest frame. Bluewood of that, there's a UV branch, and redwood of that, there's an optical branch that rises. Okay. A lot of the initial interpretation by many of these papers, and even till today, says that, well, this is it's some combination of reddening by dust. Okay, that's when you see something red, that's typically what people think about. And then but some fraction of the photons, scatter out, presumably by dust scattering or electron scattering. Okay, so this is scattered blue light, but most of the energy is buried. Okay, what is buried? Okay, it could be a galaxy, it could be an AGN, and then the favorite, of course, is when you don't know, it's some combination of the two, right? Which is really not helpful. Okay, okay. But I've never found this initial explanation very satisfying, or let's just say that I was secretly hoping that it was wrong. First, it's implausible to me, because if it was really just dust, okay, oh my God, I'm sorry to all you dust people, okay? Dust is great, but what a nuisance, right? I mean, then I haven't learned anything, okay? But I don't think it's dust. I don't think it's scattering, because this SED is quite universal. That is, this very small dispersion. That should not happen for dust grains or scatterers. That's an environmental thing. It's kind of like, over Taipei, right? Today is clear. Yesterday was a little more cloudy, and then maybe tomorrow will be thunderstorming. There should be a distribution of covering factors and optical depths. Okay, it's hard to imagine how you could coordinate them, almost always to produce this universal shape. So instinctively, I was really thinking, but also hoping that it's something else. But if it's something else, then we have to think of something really new. Because that's very hard to imagine what could produce something like this. So there are many ideas of involving neophysical scenarios, which is what I'll come back to near the end. Okay. The other aspect, besides this UV optical SED being like this, is the fact that there are no X-rays. Despite the fact that these fields were selected, of course, to have the deepest Chandra observations, and people look at all the counterparts, no X-rays, you stack them however you like, multiple papers of ways of stacking, no detection. That could be a problem if you want the AGN idea, right? Because they're supposed to have X-rays, unless they're really super Eddington, but in which case they still should have some X-rays, right? And to date, there's also no radio emission. So both of these are not potentially in conflict with the AGN interpretation. But I'll show you later that it actually isn't, okay? Okay, so this is just the early stuff. By early, I mean 2023, 24, okay? This field moves very fast. But the most significant observation, of course, is the spectroscopy, okay? JWST is not only an amazing imager, has amazing spectroscopic capabilities. I think the earliest and most influential paper is by Jenny Green. And you can look at the spectra, and the most important first realization is that these objects are extragalactic. 70 to 80% of them are outside of the Milky Way. They didn't have to be. Because it turns out that these little red dots with these kind of SED looks very similar to brown dwarfs. They could have just been a population of brown dwarfs. And in fact, 20 to 30% of them are brown dwarfs. But the majority of them are not. They're extragalactic, and they're very, very far away. Redshift 4, 5, 6, 7, 8, 9, even 10. Okay, very far away. If you look at the spectra, they basically, to zeroth order, look like so-called type 1 AGNs, right? Broad emission lines, thousands of kilometers per second. Okay, and these lines are not detected, they're not 3 sigma detections. You can see these are very, very good measurements. Okay, this is very significant measurements. If you simply use the virial mass estimates that we apply for AGNs and quasars in the local universe, you would deduce black hole masses in the range of 10 to the 6, 10 to the 7, 10 to the 8 solar masses. So there's very massive black holes. I remind you, the Milky Way is 4 million, and M31 is 40 million. Okay? So these are not the seeds that I talked about. These are not the 10 to the 4, 10 to the 5 solar mass, direct collapse seeds. Those are 10 to the, that's factor of, 100, 1,000 less, okay? If you just naively take the luminosities and try to estimate the Eddington ratios, they're respectable, okay? They're high to even Eddington or super Eddington. And without being very quantitative, if you're used to looking at AGN spectra, you'll realize that the metallicity is very low. Okay? There's essentially no metal lines apart from O3 5007. But that's because O3 5007 is a very, very efficient coolant of the ISM in the optical. Okay, so even the most metal poor dwarf galaxies, the strongest sign is O3. So you only need a tiny bit of oxygen. Okay. So you have oxygen for sure, but basically nothing else. Okay, so extremely low gas phase metallicities. Are we sure that these black hole masses are reliable? Actually, no. Okay, so we use these simple scaling relations based on local AGNs calibrated from reverberation mapping. Who knows if this applies to this regime, okay? In fact, there's a warning that came from gravity, okay? This is a very impressive observation from the MPE group. There's a redshift 2.3 quasar, okay? Very far away, okay? They're actually able to resolve the broadline region and obtain a dynamical mass of the black hole. Without going into complications, let me just say that this black hole mass is a factor of a few, like 3 or 4, lower than the naive black hole mass you would estimate from here. So it could be, especially if these things are all super Eddington, that the black hole masses are systematically low by a factor of a few. But that's about it. Okay, I do not buy for a single moment, as many papers in the literature try to argue, oh, the masses could be orders of magnitude wrong. Okay, I don't know what they're talking about. It's just a basic fact. Okay, unless JWST screw up their flux calibration and they screw up their wavelength calibration, there's no way to wiggle yourself out of the fact that these things have luminosities of this range. Okay, and this immediately implies a mass of that order. Okay, I mean, gravity is the most efficient way of converting, mass to energy, much more so than nuclear reactions and chemical reactions for sure. Okay, so while the masses are not necessarily accurate, okay, they are large. They're large, okay, on this ballpark. But is it this? a single object, or is it a cluster of smaller things? This cannot be ruled out. We have no idea what interesting things lurk, in the early universe, okay? By the way, these are precisely the same sets of arguments that were, discussions that were made in the first big meeting held after the discovery of quasars, 3C273, okay? The huge luminosities. But what is it, right? Where is it coming from, okay? Huge luminosity means large mass, that's kind of trivial. But is it this or is it this, okay? So the key observation, most important observation is this one. It's the fact that some of these objects vary. If it's a cluster of subcomponents, they would not vary. Okay? I'm not saying they all vary. It's a complicated story why, even if they were, it would be difficult to detect. You realize JWST has not been operating very long and they're not designed for obtaining accurate light curves, okay? But some of them, no doubt, vary. Okay? So that, to me, is one of the most important observations to date. That then tells me that at least some of these things are not just massive, but it's a single compact object. Okay. The other really astounding thing about little red dots is that they're all over the place. These JWST fields are tiny, they're pencil beam things, okay? And yet hundreds have been discovered already. And I told you 80% of them are at high redshift of broad lines, right? So to be exact, this is two different redshift ranges, okay? So shown here in green is the luminosity function, the space density of quasars, okay? Quasars stop over here. This is just extrapolated luminosity function. You can see the little red dots are 100 times more abundant, okay? The blue line here is the space density of all galaxies discovered in the same field at those same redshifts. And you can see that these objects are approaching sort of a few percent, even up to 10% of the galaxy population. That's extraordinary. There are a lot of these things. And surely there are others that we just haven't found yet for various sensitivity limits, right? Okay, so, but in hindsight, are you actually that surprised? In hindsight, no, okay, because I told you in the local universe, the occupation fraction of massive black holes is very high, right? More than 50%. So where did you expect that these dead black holes, when were they formed? Well, now, right? And where? Well, among all the high redshift galaxies. So basically, I think this is the earliest stages of the things that will become the supermassive black holes that we have known for 25 years in the local universe. Another much talked about property of these little red dots is that they have extraordinarily overmassive black holes. Okay, so the way to show this is, again, this canonical scaling relation, galaxy mass versus black hole mass. This is the local scaling relation. And all these objects lie a factor of 10, 100 above it. Okay. This is a very generic property of this class of objects. So there are two ways of looking at this. Okay, most people like to discuss in terms of the black holes being overmassive. Another perspective, and they're not equivalent, depends on what you're interested in, is that the galaxy is undermassive. Okay. In either case, whatever your viewpoint, whatever your interest is, clearly the black hole, stole the show as early as possible, and the galaxy has a lot to catch up. Okay, so what's the chicken and what's the egg? Okay, well, I don't see any chicken, ladies and gentlemen. What I see is a big, giant egg. Okay. I think this poses actually a pretty serious challenge for the 20 odd years of literature on feedback and coevolution, where things, people went out of their way to synchronize things and, right, into everything evolves in lockstep or whatever. many flavors of those types of models, but none of them predicted this, let's just put it this way. So I think one has to go back to the chopping block for those types of issues of feedback and so forth. So this is a much talked about result, but I should interject some cautions. Yes?
Without seeing the underlying galaxy, how do you determine this?
I'm sorry?
Without seeing the underlying galaxy,
Yeah.
how is the mass?
Yeah, very good point. I have no idea. This is not my paper, okay? I will show you in a minute that these numbers are really wrong. I'll show you the proper way to do it. I'm building up to some recent work. Yes, please.
I wasn't really any idea what.
I'm sorry?
Well, two questions actually. The first one would be, do you have any idea what destroyed the black hole that much? Because if we see them, you say they're really accreting, what do they have to accrete?
Yeah,
And the second question is kind of related. I wondered if anybody is looking at like in which kind of galaxy and environment these things live. Is it a different kind of environment, or they found predominantly in like water cluster, or
yeah. I'm not trying
they
to.
are just like
Sorry, I'm not trying to be rude to blow my nose, but yeah, I'll come to all these issues. It's part of my talk, so just hold on for a second. Great questions, though. Okay. So I told you that the black hole masses are not accurate, but not terribly wrong. But I'm actually even more suspicious of the so-called galaxy. Okay, you just asked, right? How do you know you can measure the galaxy? I can tell you for absolute certainty that with the Hubble Space Telescope for high redshift quasars, it was not possible. It was never possible for high redshift quasars. Not only because the PSF was fatter, but you were dealing with the rest frame ultraviolet, even in the H band. Okay, so try as you might. Okay, here's the quasars, the PSF star. You know, it's not like there's nothing. It's just that the residuals are overwhelmed. Okay, so impossible to do high redshift quasar work with HST. JWST, of course, you can do much better, but this is what I call much better. Right? You know, you have to have a little bit of faith that this is a reliable detection, and remember what you want is a stellar mass. What this is at best light, right? Okay, so you actually need a colors or SED in order to get stellar masses. So very hard, even with JWST. Actually impossible for most published works from JWST. The highest redshift quasars, these are all just non-detections. And this is a claim detection. Again, you have to really love the subject to believe that this is something you can publish a paper on, okay? Okay, so I'm not faulting the authors, it's just this is a very challenging problem, even with JWST. And with the little red dots, it's even harder because by selection, they are dots. Okay? You already set up the problem to be very hard. Okay? So realizing this, I made this as part of the PhD thesis of Li Ranzun, who just finished and is at the MPE as a postdoc. And what he did is he's developed a series of new tools. This is maybe the most significant, called GalFit-S. So some of you may know GalFit, which is a 2D image analysis decomposition tool. The S stands for spectra. So basically, it's you can think of it as a 3D, version of GalFit. And the idea is very simple. If I have a system that's composed of different blended components, for example, a disk and a bulge and a nucleus, okay, their spectral energy distribution often is different, right? So the stars here are red, these are young. An AGN is also blue, but it's blue in a different way than young stars because it's a power law and not an O star, okay? So by applying what we call astrophysical priors to help with the decomposition, we can guide the solution towards much more meaningful host galaxy decomposition. And simultaneously, we obtain physical parameters like star formation rates, ages, and stellar masses. So this is really the key new tool. And my PhD student, Chen Changhao, applied this to a first sample of little red dots. Okay, it's a kind of a boring result. Basically, we detected nothing. Despite months of effort to improve the PSF, for example, and reducing the data in ways that never been done before by the original teams, okay? I won't bore you with the details, okay? But let's just say we did everything possible to squeeze the most information out of these exquisite images. The bottom line is still, I'm sorry, this is kind of complicated. Just look at the words here, okay? Nothing detected. No host galaxy emission detected. But in addition to that, we're able to put a stringent upper limit on the nothingness. We do it by simulating the system with real galaxies in the field, in the same redshift. Okay, so we don't have to imagine what the galaxy looks like. The only prior is that the host galaxy should resemble the general galaxy population. I think that's a reasonable thing. We have no right to invent something imaginary, right? So we use real observed galaxies at those redshifts with a range of masses, and we manually insert the nucleus of, okay, and then we determine the when it peaks out. Okay, so that's the meaning of an upper limit. Okay, this is the summary. Okay, so there's a famous plot again: stellar mass on the x-axis, black hole mass. And let's just focus on the red points because those are our measurements. These are the green points that are still to be reevaluated. These are other people's measurements, okay? And I want you to see that all of these points have an arrow pointing to the left. Now, the original published stellar masses from other authors are also in red, but these are the open symbols. Here's an extreme example. Somebody claimed that this thing had a stellar mass of 10.7. Detected. Our upper limit is over here, okay? 8.3. And it's an upper limit. You can be really, really, really wrong. It's the same data, okay? It's just subject to rigorous analysis. It's a message for graduate students and postdocs, okay? If NASA gives you a $10 billion gift, okay? It pays to really treat the data with the full respect and care that it deserves. So you can squeeze the absolute bejesus out of it, okay? And these things have no host galaxies. These are upper limits, okay? I cannot say that there's no host, but they're really, really extreme, okay? But there's a very interesting aspect to the little red dots, even though there's no stellar light, that could be construed as a host galaxy. 50% or so, half of them, a lot of them, okay, has this little extension to the side. There's a little bit of a blue, fuzzy thing coming off on the side. It always comes off on one side, almost like a jet, or maybe it's an inflow or whatever. It's not symmetric, okay? Here's another one. A lot of them, very, very, very common, okay? And we don't know what it is. Is this just stars? For example, is this a satellite galaxy? Perhaps, okay? Is it just projection? That would be uninteresting, right? Or is it a real neighbor? If it's gas, is it inflowing, outflowing? Okay, not much is known. So here's the second work by Chen Changhao, which is a definitive work on this subject, because he used not 7, but all 17 bands of NIRCam. NIRCam actually has other bands, the medium bands. Okay, medium bandwidth filters, okay? And one of them happens to coincide with oxygen 3 5007. Okay, very convenient, okay? So again, too much detail, but basically we're able to very, very clearly distinguish between the SED of a galaxy, that is stars, versus an SED that is just pure nebula emission. This is just pure ionized gas. Okay? And we are very certain that this model is superior to this model. Okay. Okay. So this little fuzzy thing coming off on the side is not stars. Okay? It's not a galaxy that is offset from the nucleus. For example, it's not a neighbor interacting with it. Okay? It's just a blob of ionized hydrogen with a bit of oxygen. The metallicity is small, about 0.1 solar. The density is about 10. Okay. Anyway, it's a cloudy model. Okay. But we're very, very sure that this is gas and not stars. Okay. So you understand what I just said. Okay. In the very best study cases, there's no evidence whatsoever for the existence of starlight.
What's the metric that says the bottom is better model? What is your position based on?
It has the SED requires 2 photon emission. Okay. It's hard to show in here. Okay, but the best fitting model contains a nebula 2 photon emission and the Balmer jump. Okay, you see, this is very different than yeah. Okay. Okay. What about dust, which was the initial motivation by the early papers? It's a busy plot. I apologize. I should really not show it like this. Let me just summarize by saying, try as you might, there's no credible direct detection of hot or warm or cold dust. Okay, this comes from the MIRI camera. The people have tried very, very hard to detect hot dust and warm dust, which you might expect from a torus. Okay, there have been many ALMA studies, many ALMA stacks. Okay, there have been attempts to detect C plus and C. Anyway, basically, no dust. That then creates a problem, right? Because now you have to explain why these things are red. Okay, but it's really fascinating. If there are no stars and there are hardly any metals, of course, it stands to reason that there should really be very little dust as well. Okay, basically, no evidence for significant dust, at least significant enough to explain this V-shaped SED. Then we're led to the inescapable conclusion that this weird SED is intrinsic. It's intrinsically red, not reddened. This is not dust reddening. It's just red. Okay, and we need to understand what possibly could be producing this. There are many ideas. Sort of every week there's some crazy model. Most of them coming from my colleague Kohei Yoshi, who loves to do this kind of stuff. But I think this is emerging to be, this is an early version. The latest one, which is much better, is from a student at Princeton, Liu Hanpu. Okay, but the idea is very simple. Okay, so you do have a central engine. You do have hot photons coming in the center, presumably from an accretion disk around a black hole. Okay, but surrounding it is there's this optically thick, dense gas envelope. Okay. It does many things, but one of the things it does is takes the UV photons and it makes this nice 5,000 Kelvin black body. Okay, this turns out that this shape, okay, is roughly 5,000 effective temperature black body. This envelope can explain this type of SED, but it can explain more. It can explain the fact that in the spectroscopy, I'll show you in a minute, another very distinctive and common feature is that there's this very prominent Balmer break. That's why the V, okay, happens at 4,000 angstrom rest frame. Okay, what is the Balmer break? You're more familiar with the Lyman break, right? Lyman break comes from hydrogen in the n equals 1 state. Now hydrogen is in the n equals 2 state. That's all it is. But in order to get it to n equals 2 and keep it there, you need to have enough collisions. You need to have high enough densities. About 10 to the 9, 10, or even 11 hydrogen atoms per cubic centimeter. Okay, so a dense gas will be able to produce this type of Balmer break. Very interestingly, these types of densities, of course, are the same densities required for the broad emission lines. Okay, so it's a sort of broadline region densities. So it explains this characteristic Balmer break, which is now an established feature of little red dots. Equally impressive is that it explains the Balmer absorption that is seen in about 20, 30, maybe even up to 40, 50% of little red dots. So this is the H alpha line. I can show you data for H beta, even H gamma. You can see there's this absorption feature. Okay. Again, to produce this type of situation, you need to have the hydrogen in the n equals 2 state. Curiously, this situation is almost never seen in the local universe. Okay, hundreds of thousands of quasars, something like 0.001% of them. Anyway, some extremely minuscule fraction show Balmer absorption. I don't think I fully understand that. Okay, but whatever the reason is, it must mean that the covering factor. Okay, the probability that, so maybe intrinsically we know quasars, they all have dense gas, but maybe the geometry is such that in these environments of LRDs, just the covering factor is just that much higher. Okay, it's tens of percent. Okay, okay, so Balmer breaks. Oh, yes.
The absorption feature that you show are asymmetric. So if you have a speed of gas, unless you have a proper motion difference, how do you explain that these features are not symmetric and the absorption features are not symmetric around Balmer break?
So usually this arises if you have some kind of outflow. Okay. Think of a P Cygni profile around a massive star or broad absorption line quasar. Okay. In fact, the mystery is not, so it's asymmetric, but particularly to the blue. Okay. The interesting thing is, in fact, these velocities are not large. You can see these are only, 1 to 2. This is an extreme example, but basically they're just a few hundred kilometers per second. Instead of the usual situation in quasar outflows, which is thousands. In fact, BAL quasars can be 10% of the speed of light, 30,000 kilometers per second. I think part of maybe the main reason that this is that these winds are very modest is because the metallicities are low. So if the winds are line-driven winds, is mostly the case, coupled with the fact that you have no dust. Okay, so therefore reduced radiation pressure. This is probably why the velocities are not so large. Here's a very clear example of this phenomenon, this well-studied LRD. This break here, this Balmer break, is very, very extreme. Okay. Initially, people were very excited. They thought this was a signature of stars. Okay, if you look at the stellar population, old stars, in fact, the Balmer break comes from the Balmer lines, bunching up. Okay, right? All the high order Balmer lines. Okay, but this type of shape and whatever cannot be explained by any known stellar population. This is not a stellar phenomenon. It's a pure gas phenomenon. Okay, and here are the various absorption lines I mentioned. So the Balmer break. Okay, the red continuum, the Balmer break, the Balmer absorption. Much less talked about, much often until it's just people just realizing this. This is, okay, I love this plot, but I'm afraid for most of you, it's not the most helpful thing. Okay. Do you know about the Balmer decrement, right? You use it to obtain reddening in optical spectra. The ratio of, say, H alpha to H beta. Case B recombination is for H2 region 2.86, okay, over here, yeah? Right? So if it's larger than that, then it's due to dust reddening, yeah? Okay? So this, unfortunately, way too complicated plot. What it's trying to show you is that the narrow component of the Balmer lines is shown here in green. You can see that they have no reddening, or just maybe just a little bit, okay, very modest, okay? But the broad component, the broad lines, which is the blue points, they have these truly huge values, okay? Okay, so most people, even spectroscopists like myself, this is like utterly shocking. Balmer decrement of 20, are you kidding, okay? Right, okay? Which if true would imply, you know, extraordinarily large amount of reddening. But it is impossible because the narrow lines are in the foreground of the broad lines. It's coming from the same system. Okay, the broad lines are in the core, and the narrow lines are in the outside. Okay, so it's impossible that this is intrinsic. I'm sorry, that this is due to dust, because the dust is not imprinted in the foreground screen. Therefore, these extreme Balmer decrements are intrinsic. Okay, there are beautiful explanations of how this can come about. I leave that as an exercise for Osterbrock and Ferland's book, for example, okay? The original ideas go back to Netzer, 1973, and so forth. But basically, in very dense media, it's been long theorized that you can achieve these types of extremely non-case B Balmer decrements. So in fact, it's all the same thing. Okay? All of these phenomena, okay? This red continuum, 5,000 Kelvin black body, the absorption, the break, the Balmer decrement can be elegantly explained just by speculating that this black hole in the accretion disk is surrounded by a bunch of dense gas. Okay, in some papers, such as this one, and also Liu Hanpu's paper, they literally mean that it's a whole envelope. Okay, so-called black hole star or quasi-star. I don't think that the data require that. The data simply tells you that this has to happen with enough frequency, okay? So the covering factor is large, but it does not require 100%. Okay, so you could have holes, you can have, you know, this could be clumpy, this could be, you know, axisymmetric, you know, whatever, okay? But H over R has to be large, okay? And very, very easily, this explains why there's no X-rays, okay? This stuff is just Compton thick, okay? So with essentially very simple, you know, sort of physics of the hydrogen atom, just invoking a density which is completely reasonable for conditions of a broadline region around a black hole, and simply speculating that the covering factor is relatively large, you can essentially explain most of the main observational properties of LRDs. Okay, so are they massive galaxies? I don't think so. So these are the common solutions that people have invoked in the last couple of years. I won't even go into the details, okay? I think the most convincing argument is that I don't see anything, okay? Never mind that you would require extremely large stellar masses and stellar densities that have never been seen, okay? If you insist that the SED and everything comes from just stars, you would require a galaxy that's 10 to the 10 to 10 to the 11 solar masses of stars, all jammed into the size of a star cluster. I think you better invent a new theory of where that arises from, and moreover, where did it go? Okay, where is it in the local universe? Is it an obscured AGN? I think if the obscuration is due to dust, there is no significant evidence for that. Okay, so I think it's not obscuration. Instead, it's essentially unobscured AGN that just happens to have these unusual features in the SED, but all of these features can be explained by a model of high covering factor, dense gas envelope. I think this is a very important new insight of how black holes began and the earliest phases of AGNs in the early universe. But maybe you haven't fully appreciated just how absolutely bizarre what I just told you is, okay? I try to impress upon you that the mass of the black hole is big, somewhere like here, okay, 10 to the 7, say. And from everything that we've known the last 30 years about coevolution, we expect a healthy galaxy like this around it, okay? This is, like Andromeda, okay, or the Milky Way. The situation for the little red dots is like that. Same black hole mass, but that's the galaxy. But in fact, I blew it up by a factor of 10 so that it will show up on the screen. And in fact, this is an upper limit. Don't forget, okay? This is not a detection, it's an upper limit. Okay, so it's basically at the resolution of this screen here. Same black hole mass, but you would admit that the galaxy around it is completely unprecedented. This is what makes this so bewildering, okay? So I just summarize in words what I just said, okay? These are pure AGNs to zeroth order with black holes of this magnitude, little if any evidence of stars surrounding them. This being the case, should we be a little bold? And let's go a little bit further and see what this means. I think we are really impressed to think about how did this thing form. Okay. Not only how did this thing form, okay, in fact, we're looking at how galaxies form. Because I just told you there's no galaxy. So if you actually want to know what the initial conditions of galaxy formation, you're looking at it. It might seem like a trivial point until you ponder for a moment. And if you understand what the literature has been, the classical literature for galaxy formation, okay? It's very different. Nobody ordered this, okay? But let me take one thing at a time. So first about the formation, okay? Because I just told you there's no stars. There's a little bit of gas, of course there is, otherwise it would not shine, right? But you don't need very much. Even, a 10 to the 7 solar mass black hole, you only need 0.1 solar masses per year to reach the Eddington limit. Okay. I think this black hole could not have formed by any of the standard baryonic channels. Okay. There are propositions in the literature, a very serious one, that we're looking at black holes that were formed from they're actually primordial black holes. Okay, I don't know anything about that subject, but I'll tell you about a model I also don't know much about. This is the work of my colleague Fangzhou Jiang. Okay, and what we propose is that this is the little red dot black hole arises from the core collapse of self-interacting dark matter. Now, before you say, oh, you've gone off to the bunkers, okay? This is, for the cosmologists, this is not a new idea. SIDM was proposed quite a while ago to explain all sorts of challenges in standard CDM, okay? Small satellite problems, the soft cores in dwarf galaxies, and so on and so forth, okay? So this is a known concept. but we want to apply it in this context. And if you think that SIDM is some really weird thing, but from the point of view of what is the real difference between standard CDM and SIDM? Okay, they're really just two extreme ends of the of interactions that obey Yukawa-like potential. In the language of these types of models, the key parameter is the cross section, the sigma, and this omega is a velocity. Okay, so the cross section falls off exponentially above a certain velocity. This is necessary because SIDM is supposed to be operating in low mass halos to explain the small scale structural problems of CDM. Okay, so these are the two key parameters: sigma naught and omega. And there's a rich theoretical and observational literature what values those ought to be. A simple point about SIDM that we want to invoke is the fact that, of course, these particles have self-interactions, so they undergo elastic collisions. Therefore, the cores of these halos, okay, because they can exchange energy and angular momentum, becomes isothermal. In a system that's a self-gravitating system that's isothermal, for example, a globular cluster, the core of a globular cluster, it will undergo core collapse. Okay, it's exactly the same. You can think of this as it's just like a globular cluster. Okay, the only question is how long does it take? Okay, if it takes forever, then it's not interesting. We want this to happen fast enough to explain the little red dot phenomenon. That's one thing. And the other is that after it undergoes core collapse, what happens to it? Of course, this is very speculative, but according to people who've done simulations, credible people from UC Riverside who actually work in this kind of stuff, these are relativistic simulations, it is said that 1% of the halo mass can collapse into a seed black hole, almost independent of the mass of the or concentration of the halo, roughly 1%. Okay, so we're running with this idea. Whether this is really true, I think it's really worth intensive investigation moving forward. Okay, but let's just take this as a given and see what happens. So what we did, or what Fang Zhou did, I didn't do anything. I was just cheerleading. Okay, is that he calculated this core collapse time, which depends, of course, on the mass of the halo, the concentration of the halo, this cross section. And what is shown here is these are contours of core collapse time. Okay, so here's 1 gig a year, half gig a year, and so forth. We want to be here, right? Because little red dots are very high redshift. So we want them to have core collapse, like somewhere around here. Okay, and that means immediately that the concentration of the halo has to be large, sort of 20, 30. These are rare halos. Okay, these are rare halos. So the key question is, are there enough of them? Okay, I'll show you in a minute. Okay, interestingly, these curves, you can see they're curved. Okay, so this is a preferred range of halo masses. Okay, right. The reason is that if the mass is too low, the dark matter density is too low, and the self-interaction is inefficient. If the masses are too high, the velocities are too high. Remember, the cross-section is velocity dependent, okay? So there's a preferred range of halo masses. This is a very nice, distinct prediction of this model, which can be falsified, right? Because if it can be shown that by some means that the halos of that little red dots live in, are much more massive, then this model is ruled out, okay? But at the moment, we don't have such data. Anyway, so this is the setup. I'm sorry, this is way too complicated, okay? But the key point is that the condition for forming such a seed by SIDM core collapse is that, of course, the collapse time has to be shorter than the time since halo formation. And all I'm showing you here is that this is only obeyed over a fairly narrow range of halo masses. Okay, so it only shows up this red region here. Okay, so it only shows up in these panels, and only at redshifts larger than this is 1 plus z, so like 9.5. Okay, so redshift 8.5. Okay, so this can occur at high redshift and only at high redshift, and over this restricted range of halo masses, sort of this range. Okay, so 10 to the 7, 10 to the 9. I told you that 1% of the halo mass, according to these existing calculations, can produce a seed black hole, then it would produce seed black holes in this range, say 10 to the 5 to 10 to the 7. Okay, it's a very, it's really a thought experiment rather than any rigorous calculation. Okay, so we're in the ballpark, and the redshift satisfies our needs. The question is, are there enough of them? I told you the halos have to be, these are not, your typical halo. Okay, they're really on the tail of the distribution of concentrations. Okay, so we have to take that into account. Okay, and also other cross sections that we're using, we actually haven't fine-tuned them. We just took typical values that people derive from, sort of standard SIDM applications, like fitting the rotation curves of dwarf galaxies. Okay, so we haven't tweaked things. We just took sort of typical cross sections that people have already been using. So with all those ingredients in hand, Fangzhou put things together and produced this plot, which practically made me fall out of my chair. This is not a fit. The data are the red points. That's the mass function, black hole mass function of the little red dots. And this pink thing is basically, best guess attempt by combining the things I just showed you. You gotta admit this is pretty good. Okay? Because it's not trivial. This is not a trivial solution. There were so many things that had to go together. Okay? So this is where we stand. Okay? It also has very distinctive predictions. Okay? So for example, because it's tied to the halo mass, right? And only operates over a range of halo masses, there should be a lower truncation to the mass function. Okay, that's potentially testable. Okay, and also, okay. Anyway, the limits of the mass function are defined by the range of halo masses. If this is true, and I really hope that this is true, okay, then we now have a powerful framework to make further predictions. Because now I've just told you which halos at which times are populated with these seed black holes. Now I can evolve them forward. So what is the future evolution of the entire halo population? That's just, basically extended Preshechter. Because the future evolution of the halo is driven by the gravity, right? Not by, I don't care about the nature of the dark matter particle. Therefore, we can make very distinctive predictions about the clustering and the assembly bias under different scenarios. So specifically, the scenario for SIDM, this is our model, okay, produces very different predictions from direct collapse, very different predictions from primordial black holes. This is Avi Loeb's low spin. Anyway, there's another model, okay? But basically, they're potentially distinguishable predictions that will come from forthcoming, actually very soon, experiments from James Webb, like Cosmos 3D. Okay, it's designed to do this. Okay, and Nexus because they have large area survey. Okay. The other thing is that surely not every single one of these little red dots, will nicely grow a galaxy around them. Right? There has to be some renegades, right? That just fail to grow. Okay, we call relics. Okay, whether we'll find them in the local universe, and lo and behold, there seems to be such a population. Let me just leave it at that. Okay, these are so-called green peak galaxies. But suppose they don't shine in the local universe, because in which case we will not find them as anything by light. Then we would have to resort to something like microlensing. I'm going way too long. I'm sorry, Satoki. Okay. So the idea behind this paper is we can use LSST over 10 to 20 year timescales, using 500,000 quasars as background sources, and it would. So of course, the microlensing light curve is not your typical, planet or thing. Okay, this has a time scale of a century. Okay. Anyway, I don't have time to explain the details. So you can look at the paper. We estimate that you can detect tens, if not hundreds, of such events. Think of it as like the Machos project, okay, from 30 years ago. Okay. Okay, I've run out of time. Right? Can I have 2 minutes?
Sure.
Yeah. Okay. Because now this is really the fun part. Just 2 minutes. Okay. I have a cartoon. So I want you to imagine what I just told you. So let's start. It's really basic. Okay. So we're talking about high redshifts. Let's suppose that little red dots do reside in the halo. Okay. So we have a dark matter halo. You have baryons in that halo. Okay. In the center, I stick in the black hole. It's a little red dot. Okay, 10 to the 7 solar masses. Because I really believe it's something like a black hole of that mass scale. But now let me be more specific. I can actually give you the parameters of this halo if it's SIDM. Okay. So I basically fixed almost everything. I told you the outer boundary conditions, and now I just told you the inner boundary conditions. But this little red dot is accreting. Maybe even super Eddington. Maybe it's a slim disk. Okay, so an accretion system has an axis. Okay, that means that the radiation that comes out is obviously highly anisotropic, and any wind or shocks, okay, kinetic energy, momentum that comes out is also highly anisotropic. So I want you to keep this picture in mind, that this is the very, very t=0 moment of galaxy formation. And I just told you everything you need to know about this, is almost everything. Okay, this is how it starts. You can tweak it, we can debate about it, okay? But I don't know how to get around what this, okay? Given this, then I would like to ask you, how would the CGM cool? Well, duh, it's not going to be isotropic, right? Just like an, O star, wants to accrete, along the equator, okay? So it breaks the spherical symmetry. But I want you to do more than just this. I want you to work a little harder and form atomic hydrogen, which generally cosmological simulations of galaxy formation never do. Okay, they reached very temperatures of 10 to the 4 Kelvin, and they say, "Wow, we process it, Kennicutt, Schmidt, boom, we make stars." Okay, you guys work on star formation. You know that's not how stars form. Okay, far from it. Okay, at the very least, you need to make atomic hydrogen. And can you go a little bit further and make molecular hydrogen? There are people in the world who do this professionally, okay? They're just maybe not in this context, okay? Okay? All right? Now that you've made this molecular disk, you have to realize that it's Toomre stable. Because you have this giant point mass potential in the center. It's not going to easily want to collapse or fragment, but eventually it better do so. What is the first generation of molecular clouds? that comes out of this disk? Is it a typical GMC, Larson's laws? You know what I'm talking about, right? I would like somebody to seriously undertake this exercise. And whatever you do, for heaven's sake, do not form stars. Yet. Because the moment you do that, you're just making a pretty movie. Not just some prescription, you just, then you do all this stuff, okay, whatever, okay, right? That's fun and worth doing, okay, but control yourself, try to not to do that. I want you to give me the initial conditions for star formation, okay? I think that would be very, illuminating, at least for me. I hope it would be to you. Because if you can do this, of course, eventually you'll form stars, there'll be chemical enrichment, feedback. Remember, JWST is seeing these, really interesting chemical enrichment abundances and so forth, right? Then this is open for discussion. So when did the first stars form? And what was their initial mass function? Is it top heavy after all? Okay. Possibly, okay, who knows, right? And what was the spatial distribution in kinematics? Okay, it's very likely, I think it's a thick disk. It's a dynamically hot, thick disk. That's geometrically thick disk. It's not a sphere, okay? It's not a thin disk, okay? And then what are the implications for early chemical enrichment, for feedback, both from the AGN and from supernovae, okay? And do you think that the dark matter halo is just going to sit there, quietly and do nothing? No, it's going to respond. The whole system is coupled and dynamic. So the dark matter halo itself is going to, come alive, okay? That in effect, in turn, will affect how the baryons, circulate and so forth. So I think this set of problems is really, really rich and really interesting. To my knowledge, I've never seen any study of this type. Not surprisingly, this red dot phenomenon was just discovered very recently. So in fact, the people in this building are perfectly set up. Are you listening, Siani? Okay. Okay. You have all the star formation people. Okay. Can somebody please work on this? Okay. All right. Let me finish. So for the students, there are 4 reviews. These are old things, but they're still relevant. And then there's a new review by Inayoshi and me on little red dots. Okay. All right. So thank you very much.
Any question? Yes.
I have 2 questions. The first one is in the last part, especially, you assume the galaxy is going to form around the middle red dot. Does it ask to be around the middle red dot? Could it be that the galaxy forms circularly and then there's an interaction between galaxy and middle red dots?
There's what?
Do you in the last part, you assume that the galaxy is necessarily going to grow around a little red dot, which may not be the case. It could be that the galaxy forms separately, and then there's an interaction between this wandering black hole and primitive galaxy.
Great idea. Write the paper tonight. Put an astro pH. Yeah, you can imagine many things. Okay, but what I think this is
Do we have any evidence that it has to be around the little red dot? Or do we have any evidence against that?
well, there's no giant population of naked wandering black holes in the local universe. I think that would have violated microlensing. So these black holes, they have to grow a galaxy. They can't be naked forever. There's so many of them, but they don't exceed the number of galaxies, which is good. Okay, so they're basically the earliest generation of AGNs. Okay, AGN. The G stands for galaxy. Okay. Yes.
I would like to come to the simple model of the red dot. didn't mention, if I'm not wrong, the mass of the ionized gas.
Yes. It's
What is the cooling time?
the mass is actually very minuscule. Sorry, I can't. Never mind. Never mind. It's just a little bit of H alpha emission. Okay, so I don't know, 10 to the 4 solar masses, 10 to the 5 solar masses. It's just a trace amount of ionized gas. Yeah.
Is that giving you a cooling time of days, or I mean, the question behind this is that allowing to separate out variability, timescales, and models for what you have seen in one of your observations?
So I think if the ionized gas is just if you don't have photoionization equilibrium, okay, so if you turn off the ionizing source, I don't remember. It's not days, okay? Guys, you've taken Frank Shu's course, okay? It's what is the time scale for recombination? It's not days, but it's not a million years. But the fact is that you have continuous heating for ionization, so it's in balance. Right?
It's acting as a low pass filter for the variability of any source inside, if I'm not wrong.
Yes.
So you could have some deductions of.
That's an excellent point. In fact, that's been discussed. In fact, this is one of the. I should have listed. This is one of the merits of this model. Okay, that in addition to explaining all these things, it potentially could also explain the weakness of the variability. Okay, but the fact is, we do see variability in some sources. That's okay. I think that just means that I think this envelope is not really a fully covering envelope. There must be some cracks in it. Okay, but that's an excellent point. So this overall picture also helps to explain why the variability is maybe weaker than you might have naively expected. By the way, the core collapse picture I just showed you has another, I think, very interesting prediction, which we haven't written about. Okay, I would naively expect a black hole to be non-spinning. It's like a ka-chunk. Okay, very different than the usual growth by accretion. Okay, so maybe that's why it doesn't have radial. If you need a spin via the Blanford-Zanaik mechanism. Yes.
Yes, I'm interested about the local energy of the little data.
Yeah.
So what are their redshift distribution? Because if they are obscure AGN, so how and abundant universe, and how did they evolve into the kind of ordinary AGN?
So you're asking about these local analogs? Redshift distribution. Okay. So the redshift distribution right now is it's a messy topic to discuss. Okay. So they seem to be found mostly above redshift 4. Definitely, that's where 4, 5, 6 is where they really peak. At higher redshift, there seems to be a genuine decline. Okay, but not non-existent. There's a redshift 10 candidate. Okay, so it seems to rise at redshift 10 or 11, peaking around 6.5 or 4, and then it drops. But I don't actually think that that drop is necessarily meaningful, because remember, this little red dot very soon will no longer be a dot. Once it grows a galaxy, which it will, okay, it's going to fall out of your morphological selection, okay, and potentially even your color selection if this dense gas environment, could change, okay, so that because eventually it has to change, otherwise you wouldn't be able to explain the SEDs of normal quasars and AGNs at cosmic noon, which do not look V-shaped. Okay, so somehow this cocoon of gas, these unique conditions early on, will change. So the SED I don't think will be preserved, at lower redshifts, and certainly the morphology will not be preserved. It's going to grow a galaxy. By that time, you will not call it a dot. So the current surveys are just not designed to address this. Sorry, the current studies. The good news is that the answer is all in the data. So what my group is now trying to do, we need help. Maybe somebody here is interested in helping us and we can collaborate. The entire history of the universe, from the earliest black holes and galaxies until today, are in these exquisite deep fields. We just have to analyze every object, democratically, uniformly, by not selecting by anything. Do not select by anything except by photoz's. Let's just get rid of the Milky Way stars, okay, and get rid of the bad pixels. Okay, that's not interesting. Okay, everything else is interesting. I don't care what it is. We don't know we didn't know what the stuff would be, right? Eventually, the population will just have to emerge. This movie has to unfold. So what do they evolve into, et cetera, et cetera? I think if every redshift bin, we have a good, mass function of the objects, right? Eventually, I think it must all, it's like a jigsaw puzzle. Initially it's like, looks like a mess, right? Eventually you're going to see the jigsaw puzzle, come together. But all of the data has to be analyzed using the same tool, the same degree of care, so that things can be properly compared. At the moment, that's not the case. Various teams do various things, and importantly, they always select by something, because that's one way to reduce the size of the sample, and it's understandable. Okay, but eventually, I think all of the data will just tell the story. Okay, so yes, sorry.
Cheyenne,
Yeah.
quick question. Do you
Yes.
expect to see clusters of lights?
Very good point. So there's been at least a couple of pairs. Okay, little red dot pairs. Okay, so binary. But that's it. Okay, so the whole clustering business is related to what I show you, for the clustering prediction. So there should be clustering, among little red dots and between little red dots and galaxies and so forth. Okay, but I think at the moment the statistics are, people write many papers still, but I don't think it's definitive. Okay, but that's really a key thing. For example, the so-called direct collapse mechanism is a very specific prediction. In order to produce this direct collapse black hole from pristine metal-free gas, okay, you basically cannot allow the gas to cool and fragment. That's the way, otherwise it will make stars. Okay, so the way to do that is you want to prevent the formation of molecular hydrogen, or you want to dissociate molecular hydrogen. You do that by exposing it to a sufficiently intense Lyman-Werner UV bands. So it predicts that next to the black hole, there should be basically a UV bright galaxy, okay, with sufficient ionizing radiation for this to happen. Well, clearly that predicts a very strong environmental, signature. That was in our plot, okay, and so forth, okay. This will be forthcoming, okay.
itself, but do you know if is there a galaxy nearby? Is there enough concentration of galaxy? Do they seem to be very isolated? Do you have anything that tell you anything about the global environment
Yeah.
in which these things form?
So gas I told you about, that's the little blue extension. 50% of them have a gas component nearby, okay? In fact, that's photoionized and energetically consistent with coming from the little red dot itself. We
I
don't,
wasn't thinking necessarily about that. I was thinking of a broader scale. Do you
well, first I'm telling you,
did you
I'm,
did you try running?
can I please answer your question? Please allow the speaker to answer, okay? So what I told you is all that we know, okay? In these deep JWST fields, there's a lot of stuff, right? Because it's crowded, it's deep, but most of it is not associated. So the key is really to get redshifts or get at least good enough photo Z's, and that's still really lacking. So as far as the large-scale environment, that is essentially the same question that I just answered. Okay, that will come from the clustering analysis. The photo Z's, I think, are really not precise enough for really, people who do cosmology. That's really not good enough. Okay, especially for these halo masses, which are not huge, right? So the velocities, okay, they're going to be, hundreds of kilometers, a few hundred kilometers per second, not 1,000. Okay, so photo Z's, I think, will not cut it. But the good news is that the Cosmos 3D Nexus, I didn't mention this explicitly, but the NIRCam has this GRISM spectroscopy. That is absolutely breathtaking. Okay, because that means that every object in the field, okay, has a spectrum. And the resolution is 1,600, almost similar to SDSS, okay? So if there are emission lines, there'll be a lot of sources. I think this problem will be addressed within the next 6 months to a year. This is why I pushed Fangzhou to post our clustering paper, like yesterday. I said, if you want to be a real theorist, you must make a prediction, okay, right? So you want to, instead of a postdiction. So hang in tight, and you can also work on this problem. The data are basically, open to the public.
Okay, so he's leaving tomorrow. So today is the last day.
No, I'm here tomorrow.
Oh, you're here tomorrow too?
I leave on Friday. Yeah.
Oh, okay.
Yeah.
Oh, then his office is at Paul's office next to me. So that if you want to talk to him, please go to his office if he's available. So okay. So thanks to Luis.